Hey, back again. Got my friend Skelly Skeleton. He's going to help us out with this sketch about weightless. Are you weightless in outer space? What do you think, Skelly? Are you weightless in outer space? I don't think so, Dr. Bones. Unless there's no gravity. He's right. So, for example, if you are orbiting the Earth in the space shuttle or in a satellite of some nature, are you really weightless? Well, let's find out. I've got Skelly Skeleton on the scale. He's got a bathroom scale here. Now, what are the forces involved here? Well, Skelly's got a weight in the downward direction, but we learned this in another segment. He's got the normal force pointing back upward. So sort of an action-reaction. When you push on the table pushes back at you. You push on the scale pushes back at you. If you're not moving anywhere, you've got a static system. We say the net force is zero. So you've got the weight and the normal force. Well, here's Skelly. He's sitting on the bathroom scale and he weighs a certain amount. He's got the normal force canceling with his weight. He's not accelerating upward or downward. We put him in an elevator, however, and we accelerate him upward. Whoa! What do you think will happen to the reading on the scale? Well, in this case, it's true that we have a weight and a normal force, but now the system is moving with an acceleration upward. So there is a net force, and that net force is the mass times acceleration. So he's moving with an acceleration. So he's accelerating upward. So in this case, he has an apparent weight that's heavier than his actual weight. So he presses down on the scale presses up at him, and he goes up, and his apparent weight will be greater than his weight as reading in a static environment. Right? So in this case, it's going to be mass times acceleration equaling the normal force minus the weight. It's going to be the force of the acceleration, right? Mass times acceleration. So in this case, the normal force, the new normal force, is going to be the weight plus that force. Right? So in this case, he's going up, acceleration upward. What happens if we go downward? So here's Skelly. He's going to be accelerating downward. Well, if he's in a free fall, what do you think will happen? We hear about weightlessness. Are you really weightless? If Skelly is falling, well, so too is the scale. And you can actually see people falling, and here he is. He's not really touching the scale. They're both falling at the same rate. So the acceleration is downward. In this case, his normal force is going to be the weight minus that mass times acceleration, right? So he's really not weightless. He still is the same weight. In this case, the normal force is different. Normal force was different going this way. Normal force will be different going this way. So you're really not weightless unless you're outside of a gravitational environment. So the space shuttle falls toward the Earth. It's in an orbit. It's orbiting around the Earth. We'll talk about this more in circular motion, but it's moving out and moving toward the Earth, right? Centripetal acceleration. But its trajectory, right, in a circle, if we sort of broke away from gravity, we would shoot out at a tangent to the circle. So you've got an outward and an inward balance, okay? So they're really falling together. So when you're on the space shuttle, you're actually falling to Earth. Wanted to talk a little bit about the inclined plane. Galileo played around with the inclined plane. Here we've got simple inclined plane. The reason I want to talk about the inclined plane is, again, the connection to the normal force. Here I've got a piece of wood, put a little hole in the wood, and I've got sort of like a fountain pen. I took the pen out and got the plastic part. I'm going to direct it into a hole in the wood, and now it's perpendicular to the wood. So the normal force is perpendicular to the surface here, right? Directed perpendicular. However, what about the weight that's hanging from here? Well, here's a weight that actually will be projected at this downward direction. All right, so weight's always going to be going downward. However, the normal force here is 90 degrees with respect to the plane, and you can change the angle of the plane. But as you can see, the weight is always directed downward, even though this normal force, kind of hard to do here, and let me do it slowly, is perpendicular to the plane. You can see how the weight is directed downward. So you can put together your vector diagram and decide if you're interested in friction or a force going upward or downward on the plane, and put together your force triangle. For example, I can say, for example, here's my force going one way, I've got another force this way, and I've got the weight going downward, all right? So you've got the forces involved here on the plane, and you've got the coefficient of friction involved with the moving objects along surfaces. So the friction is going to be the coefficient of friction multiplied by this normal force. So again, normal force perpendicular to the surface, no matter how I change the angle, here this is called the angle of inclination, doesn't matter, it's going to always be perpendicular, and the mass or weight is going to be directed downward. So you can play around with the mathematics at your leisure. Interesting use for the normal force. See you in the next segment. Take care. Bye for now.